Hello everyone. Let's continue with lecture number 3. In the previous session, we talked about sets, and today we are going to finish this discussion and we also continue with functions. So, one of the operations on sets is called union. This much is very similar with the disjunction in logic that we talked about, like the union of the sets A and B denoted by this notation. And what do we mean by that? This is the case that is the set that contains those elements that are either in A or B or in both of them. So exactly the same situation as we had for disjunction. Take a look at this one. So when you want to define it, first of all, we define it inside the curly brackets for sets. So this one is a set X such that X belongs to A, or based on the disjunction that we had, X belongs to B. And at the same time, if one of them is true, the whole thing is true. And what about the intersection of the sets? We can denote it by this notation, and this is related to conjunction. It means that X should belong to both A and B at the same time. Otherwise, this proposition is false, right? So you can denote this intersection of the sets like this, which is itself a set. By looking at the Venn diagram, it's easy to recognize them. On the left side, you can see the union of A and B. And here you can see the case that X, for example, should belong to both of the set at the same time. Now, two sets are called disjoint if their intersection is the empty set. So it means that they don't have any common elements inside them. So look at these two sets. A, and it contains these elements, and B contains this one. And when you compare them, you can see there is no common element between them. So intersection of A and B would be empty set. And if this is the case, we can call them disjoint. So A and B are disjoint sets. And when we talk about difference of sets, we can denote it like this. In some books, they show it like that as well. It means that assume whatever you have inside X, check it with B, whether this is inside B or not. Whenever it is, then eliminate that one. So you can also show it by this proposition. X belongs to A, and at the same time, it should not belong to B. It's easy to see that in Venn diagram. I will show you. And whenever we talked about complements of the set, we mean, for example, for A, whatever you have inside A, you should not consider inside the complement of that one. Sometimes you show it with a line over it, like a bar, or sometimes with C over it, and sometimes with a prime. It doesn't matter which one you use, but inside the book, they use A bar. And you can use the same as well if you like. And we already defined universal set. It means that how should I know which elements don't belong to A? So it should be belong to somewhere, and that's the universal set, which has all the elements that we can think about. So of course we can define universal set the way that we want. For example, we can define universals as just natural number. That's it. That's all our universe. So you can even limit your universal set. It depends on the program, and we will talk about it in the weekly assignments too. You will see that. The examples, that would be the best to show you. Now take a look at this Venn diagram for difference between sets. So assume that you have the set A, then you should subtract whatever you have from A, but considering B. So in another word, you can say X should belong to A and not belong to B. So A minus B can be shown like that. And whenever we talk about complement of A, it means that consider whatever inside the universal set which doesn't belong to A. There are some important laws that you can see here. You can take time and go through all of them. For example, intersection between A and universal set. It is always A, because A is a subset of universal set. But take a look at the second one. Now, union of empty set with A, this one is A. Why is that? Because empty set is a subset of any set that you can imagine. So it doesn't matter what is A here. The answer again for this union should be A. So there are some laws that you can see here, and of course there are proof for them. In the book also it mentions some of them. In mathematical books you can see the proof of all of them, but it's nice to know about them anyway. So it's good to know, for example, that when we talk about complement of a set, it will give you again the same set. So please go through them. And as an example, we can consider the membership table. This table is very similar to the one that we had for truth table before. When we use it for binary system, then you could see a similar format. Now, since you know, for example, union corresponds to disjunction and intersection corresponds to conjunction, so it's very easy to know what's the value of this one out of these three, right? So you can also go through this example to remind yourself about the table of truth. If you want to talk about not just two sets, but so many sets, or maybe even 3 sets only, then you can generalize what we talked about unions, and you can show it by this notation. See? Like for example, summation, whenever you use it, you use the starting point and to the end point. This is the same scenario. You can say from 1 to n, just consider the operation union. So for all AI, I can do that. What does it mean? It means that A1, A2, A3 until AN, consider the union of them. And I can say exactly the same about intersection, of course. For our next assignment, I will give you one example related to this, and it will be useful. Okay, guys, let's start our conversation about function. Actually, it's not a conversation because I should keep talking about it. But anyway, we will talk about function. But let me pause a moment to stop recording, then I will start with function.